The evolution of wireless network security is fundamentally linked to advances in both mathematics and hardware engineering. In practical systems, achieving secure and efficient cryptography depends on the ability to carry out field arithmetic at high speeds with minimal resource consumption. Within the elliptic curve cryptographic framework, three core operations must be optimized: addition, multiplication, and inversion within a finite binary field. Each of these operations has been the focus of rigorous research and practical design, with the goal of delivering maximum speed and efficiency for the unique demands of wireless communication environments. In binary extension fields, each field element is represented as a polynomial, and the primary operations can be realized using simple hardware logic. Addition and subtraction become identical operations in this context, performed using exclusive OR gates on the coefficients of the polynomial representations. This means there is no need for a carry chain, resulting in a dramatic simplification of the circuitry and a reduction in delay for every addition or subtraction step. Furthermore, in these fields, every element is its own additive inverse, which allows for further simplification of the algorithms and hardware. Multiplication in a binary field is a more complex operation, involving the product of two polynomials reduced by a special reduction polynomial defined by the system's parameters. To speed up this process, advanced multiplication algorithms group polynomial terms and use sequential shifting and reduction, breaking down large, unwieldy calculations into manageable steps. Hardware implementations often use lookup tables and pipeline structures to accelerate these computations, ensuring that multiplication can be carried out in just a handful of clock cycles. A crucial challenge in field arithmetic is inversion, the process of finding a multiplicative inverse in the binary field. Naive approaches to inversion are relatively slow and resource intensive, which could potentially create a bottleneck in cryptographic computations. To overcome this, designers have adopted specialized algorithms such as the Ito-Tsuji inversion method, which relies on a series of squarings and multiplications. This technique allows the same hardware units used for multiplication and squaring to be repurposed for inversion, minimizing the need for additional circuitry and keeping the design lean. As a result, inversion can be performed at speeds comparable to multiplication, and the entire scalar multiplication process benefits from this efficiency. Optimizing the squaring operation is another important design goal. Squaring is a specific case of multiplication, but it can be performed much more efficiently with the right hardware design. By leveraging the structure of binary polynomials and using dedicated combinational logic, squaring units can produce results in a single clock cycle, further improving the overall speed of cryptographic processors. Hardware designs for these arithmetic units are assessed by the number of clock cycles required for each operation, as well as their resource footprint. How many logic elements, lookup tables, and flip-flops are needed on a programmable device or integrated circuit. The trade-off between speed and hardware cost is carefully balanced to ensure that wireless devices, which often operate under severe resource and energy constraints, can still provide strong cryptographic security. The efficiency of these arithmetic operations directly impacts the performance of higher-level cryptographic protocols. For example, the elliptic curve digital signature algorithm and related protocols require repeated execution of scalar multiplication, which involves many field multiplications, squarings, and a few inversions. By minimizing the cycle count and hardware footprint for each operation, the total computation time for signature generation or key exchange is dramatically reduced, making secure wireless communication feasible even on small, battery-powered devices. A notable architectural innovation is the adoption of projective coordinate systems for representing points on elliptic curves. Traditional affine coordinates require a costly inversion for each point addition or doubling operation, which limits performance. Projective coordinates eliminate most of these inversions by introducing an extra coordinate, enabling all but the final result to be computed using only multiplication and squaring. Several variants of projective coordinates have been developed, with the Lopez-Dahab system offering a particularly effective balance of speed and hardware efficiency for binary fields. In the Lopez-Dahab projective system, points on the curve are represented with 3 coordinates instead of 2. This approach transforms the algebraic formulas for addition and doubling, allowing the use of optimized field multipliers and squarers at every step. For the most common cryptographic operations, the total number of required field multiplications, squarings, and additions is sharply reduced compared to affine methods, and almost all inversions can be deferred until the end of the computation. The performance gains from these innovations are significant. In practical hardware, the use of projective coordinates and optimized field arithmetic can cut the total computation time for scalar multiplication by more than half compared to traditional methods. This improvement is crucial in wireless network environments, where latency and power consumption are critical constraints. Another layer of optimization involves the way the scalar value in the multiplication is represented and processed. By recoding the scalar using non-adjacent form, it is possible to reduce the number of required addition operations, since this representation minimizes the number of non-zero bits. The tau-adic non-adjacent form, specifically designed for Koblitz curves, goes even further, replacing many doubling steps with simple squarings thanks to the properties of the Frobenius map on these curves. Together, these mathematical and engineering advances create the foundation for modern wireless network security. The combination of efficient binary field arithmetic, optimized hardware design, projective coordinate systems, and clever scalar recoding techniques enables real-time cryptographic protocols on devices ranging from mobile phones and sensors to base stations and routers. As the demands on wireless networks continue to grow, these foundational techniques ensure that security can keep pace, delivering robust protection for data and communication in every environment. Building a high-performance cryptographic processor for wireless network security begins with the design of the hardware that performs arithmetic operations in binary extension fields. These operations are the foundation of all elliptic curve cryptographic systems and are crucial for ensuring both speed and security in wireless and mobile applications. The multiplication operation, which dominates the computation time in elliptic curve cryptography, is handled by specialized multipliers. One effective approach uses digit serial architectures based on lookup tables. In such a design, input polynomials are divided into manageable segments, or digits, allowing the multiplication to proceed sequentially with each digit processed in parallel using pre-computed results stored in tables. This enables the hardware to quickly calculate intermediate products and combine them using modular reduction based on the system's predefined reduction polynomial. The digit size, or the number of bits processed at each step, is carefully chosen to balance speed and hardware resource usage. Larger digit sizes reduce the number of cycles needed for multiplication, but require more complex and resource-intensive circuits. To further improve the speed and efficiency of multiplication, designers implement pipeline structures and buffers within the data path. These allow different stages of the multiplication and reduction process to operate concurrently, minimizing idle time and maximizing throughput. This is particularly important in high-demand applications where many cryptographic operations must be processed in rapid succession. The squaring operation benefits from even greater efficiency. Because squaring a binary polynomial involves only doubling the exponents of each term, a dedicated squaring unit can be built using simple wiring and logic gates. This allows the squaring to be completed in a single clock cycle without the need for additional computation. The result is a dramatic improvement in the overall performance of the cryptographic processor, as squaring operations are frequent in scalar multiplication and other elliptic curve algorithms. The inversion operation, as described previously, is implemented using advanced algorithms such as the Ito-Tsuji method. By leveraging the existing multipliers and squaring units, the inversion process becomes much faster and more efficient, eliminating the need for bulky, specialized hardware dedicated solely to inversion. The method proceeds by computing repeated squarings and multiplications in a specific sequence, reducing the total number of steps required compared to traditional approaches. Hardware prototypes of these arithmetic units have demonstrated impressive performance metrics. For example, with carefully selected digit sizes and pipeline data paths, field multiplication over commonly used binary fields can be completed in just a handful of clock cycles. Squaring operations are virtually instantaneous, and inversions, once a performance bottleneck, now take only a fraction of the time needed in older designs. This high level of efficiency means that elliptic curve scalar multiplication, the core operation for signatures, key exchange, and encryption, can be executed rapidly enough to support real-time communication even in resource-constrained wireless devices. In addition to arithmetic units, the cryptographic processor requires comparators and adders to handle binary field addition and equality testing. These components are implemented using arrays of exclusive OR gates for addition, with zero detection logic for comparison. Since addition in binary fields is simply a component-wise XOR, the logic is straightforward, fast, and consumes minimal hardware resources. The control logic of the processor is organized hierarchically. At the lowest level, a microsequencer manages the routines for point doubling, point addition, and inversion on the elliptic curve. This sequencer orchestrates the loading and unloading of operands, directs the sequence of arithmetic operations, and handles the storage of intermediate results. At a higher level, a state machine processes the scalar value used in multiplication, invoking the appropriate routines in the sequencer according to the chosen scalar representation, such as binary non-adjacent form or tau-adic non-adjacent form. The processor's data path connects the arithmetic units and storage registers, allowing operands and results to flow efficiently between them. Dual-port storage units and input buses allow operands to be loaded in parallel, reducing delays. The output of the arithmetic units can be directly routed back into storage or passed to other units for further processing. Careful management of the data flow minimizes latency and ensures that the processor can keep up with the high demands of secure wireless communication. Within the cryptographic system, the choice of coordinate system for elliptic curve point representation is another critical factor affecting performance. The Lopez-Dahab projective coordinate system, for example, is widely used in high-speed hardware implementations because it minimizes the number of costly inversion operations while keeping the number of required multiplications and squarings low. In this system, each point is represented by 3 coordinates instead of 2, and the conversion between affine and projective representations is performed only at the beginning and end of the computation. Throughout the main computation, all operations are carried out in projective coordinates, enabling fast execution using only multiplication, squaring, and addition. To optimize scalar multiplication, the scalar value is often recoded into special forms. The non-adjacent form, NF, reduces the number of additions by ensuring that no 2 non-zero digits are adjacent, while the tau-adic non-adjacent form, tau-NF, is specifically designed for use with Koblitz curves, leveraging the Frobenius endomorphism to replace many doubling steps with squarings. Both techniques result in fewer overall arithmetic operations and improved throughput. By integrating all these architectural and algorithmic innovations, the cryptographic processor is able to deliver secure high-speed elliptic curve operations required for wireless network security. The resulting system can support authentication, key exchange, and data encryption protocols efficiently, providing the robust security needed in modern wireless and mobile communication networks. Achieving top-tier wireless network security depends on a robust architecture for elliptic curve scalar multiplication, which is the backbone of most modern cryptographic protocols used in wireless and mobile communication. This scalar multiplication process is what enables secure signatures, key exchanges, and encrypted data transfer in the context of digital communications. The core architecture of an elliptic curve cryptographic coprocessor includes several dedicated finite field arithmetic units, tightly integrated memory for storing field elements and curve points, and a layered control system that orchestrates all cryptographic routines. The heart of this architecture lies in 3 primary hardware units: the multiplier, the squaring unit, and the adder, each engineered for the specific requirements of the chosen finite field and reduction polynomial. By equipping multipliers and adders with dual input ports, both operands can be loaded simultaneously, reducing load times and supporting rapid execution of complex operations. Meanwhile, storage modules are designed with dual output ports, enabling multiple operations to proceed in parallel and minimizing data movement bottlenecks. At the highest level of control, a state machine is responsible for parsing the scalar value that determines the number of point additions and doublings required in scalar multiplication. This state machine calls upon a microsequencer, which holds low-level routines for elliptic curve operations, such as point addition, point doubling, and field inversion. This hierarchical division of control simplifies design, increases modularity, and ensures that even as the scalar changes or new curve parameters are introduced, the processor can maintain high throughput. Field element storage in the cryptographic processor plays a dual role. It acts as a staging area for operands required by the arithmetic units and as a buffer between the high-speed internal data buses and the external, often slower, data interfaces, such as those connecting to the main processor or memory system. Efficient storage design is crucial as it directly affects how quickly cryptographic computations can be set up, executed, and finalized for use in higher-level network protocols. All logic associated with finite field arithmetic is tailored for the exact field size and reduction polynomial defined by the cryptographic standard in use. Internal computations are performed using projective coordinates, specifically the Lopez-Dahab coordinate system, which is optimized for speed and resource efficiency. While the system is flexible enough to support generic elliptic curves, it is tuned for especially high performance on Koblitz curves, which offer additional computational shortcuts. The benefits of this architecture are clear when considering cryptographic operations in practice. For example, when many wireless clients must authenticate with a central server simultaneously, the burden of scalar multiplication can quickly overwhelm a standard processor. Offloading this work to a dedicated cryptographic coprocessor, where specialized hardware performs all arithmetic operations in parallel and at high speed, means that authentication and key exchange protocols complete quickly and reliably. In the case of the hardware discussed here, scalar multiplication can be completed in fractions of a millisecond, well within the requirements for real-time wireless security protocols. An additional layer of efficiency is introduced through the use of different coordinate representations. The Lopez-Dahab projective coordinate system is chosen because it allows most of the costly inversion operations required by the affine system to be replaced with faster multiplications and squarings. When adding 2 points or doubling a point on the curve, the system relies on specific equations that minimize the total number of field multiplications and squarings, maximizing throughput. In mixed coordinate computations, where one point is held in affine coordinates and the other in projective coordinates, further optimizations are realized, especially in point addition routines. The processor's routines for point addition, doubling, and inversion are implemented as sequences of field multiplications, squarings, and additions, with only a single inversion required at the very end of the scalar multiplication process. This deferred inversion is a direct result of projective coordinate use and significantly accelerates the overall computation. Scalar values for multiplication can be represented in various ways, with different encodings offering different performance benefits. The standard binary method, non-adjacent form, and tau-adic non-adjacent form are all supported. Non-adjacent form encoding, for example, reduces the average number of required point additions by spreading out the non-zero bits of the scalar. The tau-adic non-adjacent form, designed for Koblitz curves, allows many of the doublings in scalar multiplication to be replaced with extremely efficient squarings, thanks to the special algebraic properties of these curves. For each representation, the processor contains algorithms to convert a given integer into its most efficient form for scalar multiplication, keeping the length and Hamming weight of the encoding low. The use of these recoded scalars, combined with the hardware-optimized arithmetic routines and the projective coordinate system, ensures that every cryptographic operation is performed as efficiently as possible. In real-world wireless network deployments, this kind of cryptographic acceleration is not just a luxury, but a necessity. The increasing density of devices, Higher throughput requirements and the demand for instant authentication and encryption mean that only highly optimized, hardware accelerated cryptographic engines can provide the necessary speed, security, and scalability. As a result, the architecture described here sets the standard for secure, efficient wireless network communications capable of defending against sophisticated attacks while maintaining the performance required for modern digital life. The integration of optimized arithmetic units and specialized control logic within the elliptic curve cryptographic coprocessor transforms abstract mathematical operations into real practical security for wireless networks. This integration not only accelerates core cryptographic processes, but also ensures consistent reliability and protection in the fast moving world of wireless communications. At the lowest level, the finite field arithmetic units, multipliers, squares, and adders work in concert, supported by a robust memory architecture that ensures operands and results flow smoothly between each component. Multipliers use digit serial methods, with each multiplication step pipelined to maximize hardware utilization. Squaring units, optimized for the unique structure of binary polynomials, deliver results instantly through pure combinational logic. Adders use arrays of exclusive OR gates, enabling rapid calculation without the need for carry logic. Inversion, historically one of the slowest and most resource-intensive operations in cryptography, is now completed efficiently thanks to algorithms such as Ito-Tsuji. This method reduces inversion to a sequence of squarings and multiplications, leveraging the same hardware already present in the processor. When additional speed is required, features such as resquaring, performing repeated squaring within a single hardware unit, further reduce the time needed for inversion. These design choices eliminate the need for bulky, dedicated inversion hardware and allow the same arithmetic units to be reused for different tasks, minimizing both circuit complexity and power consumption. All these field operations feed into the higher level routines for elliptic curve point addition, doubling, and scalar multiplication. The control logic's microsequencer reads each instruction, orchestrates the necessary arithmetic steps, and manages data movement across the storage and arithmetic units. Dual input and dual output storage architectures keep the data pipeline full, ensuring no component sits idle. Scalar multiplication, the cryptographic process at the heart of wireless authentication and key exchange, benefits from several layers of optimization. Projective coordinates, specifically the Lopez-Dahab system, allow most of the expensive inversion operations to be replaced with faster multiplications and squarings. The only inversion typically required is a single one at the conclusion of the computation, when the final projective result is converted back to affine coordinates. For the scalar value used in multiplication, the processor supports a range of encodings. The traditional binary expansion of the scalar is widely used, but for additional efficiency, the non-adjacent form and tau-adic non-adjacent form encodings are employed. These encodings lower the average number of non-zero digits in the scalar, reducing the number of costly point addition operations required in scalar multiplication. This not only boosts performance, but also adds a layer of resistance to certain side-channel attacks, since the number and pattern of executed operations become less predictable. Within the processor, each step of scalar multiplication is executed by a tightly controlled sequence of arithmetic operations. For binary and non-adjacent form encodings, this means a mix of point doublings and point additions. For tau-adic non-adjacent form, special properties of Koblitz curves are used, with many doublings replaced by extremely efficient squarings, made possible by the Frobenius endomorphism. The hardware takes full advantage of these algebraic properties, allowing even faster execution than would otherwise be possible. The performance and resource cost of these systems are carefully measured and tuned. Designers analyze the number of clock cycles needed for each operation, the total hardware required on the chosen platform, and the impact of each optimization. Prototypes using field programmable gate arrays have demonstrated that these cryptographic processors can execute elliptic curve scalar multiplications in just fractions of a millisecond, fast enough to meet the real-time demands of wireless authentication and encrypted communication. The overall architecture is flexible, supporting a range of elliptic curve parameters and allowing for adaptation to new standards and security requirements as they arise. The processor is optimized for the most commonly used NIST-recommended binary fields and curves, but can be adjusted for alternative parameters as required by specific applications or future cryptographic research. In real-world deployments, this level of optimization and flexibility is indispensable. Wireless networks must handle authentication and key exchange for thousands, sometimes millions of devices, all requiring rapid, secure communication with minimal delay. The specialized hardware and software integration described here is what makes robust, scalable wireless security not just possible, but practical. The result is a cryptographic engine capable of supporting the most demanding applications in wireless networking, whether that means securing personal mobile devices, authenticating users in public hotspots, protecting critical infrastructure in industrial environments, or enabling encrypted communications for the Internet of Things. The architectural foundation established here forms the backbone for secure wireless communication today and sets the stage for ongoing innovation in network security. The implementation of this cryptographic architecture reaches its fullest potential in the context of real wireless network security protocols. Wireless communications present unique challenges not only because of their open and dynamic nature, but also due to the diversity of environments and devices involved. Mobile phones, laptops, sensors, industrial machines, and critical infrastructure systems all connect wirelessly, often relying on different protocols, standards, and operational constraints. The cryptographic processor must be able to meet the security needs of all these use cases while maintaining performance, efficiency, and scalability. Wireless network security protocols can be grouped into several broad categories, each presenting its own set of requirements. General wireless and mobile networks focus on universal authentication, key exchange, and data protection. In these settings, the cryptographic processor provides the mathematical foundation for establishing trust, encrypting communications, and safeguarding information as it moves through the airwaves. For wireless local area networks, the processor supports protocols that handle rapid user handoffs, roaming, and secure access control across domains and service providers. A separate and particularly demanding area is ad hoc and sensor networks. In ad hoc networks, devices must establish secure communications without relying on fixed infrastructure. This means that the cryptographic processor must support decentralized authentication, key management, and secure routing protocols that can adapt to changing topologies and unpredictable connections. Similarly, wireless sensor networks introduce the challenge of extremely constrained devices with minimal computational resources and power reserves. Here, lightweight cryptographic routines, efficient hardware architectures, and adaptive security mechanisms are critical to protecting data and ensuring network integrity. Within all these scenarios, the optimized cryptographic processor becomes the silent engine driving every secure transaction. Each time a device authenticates to a network, every time encrypted data is transmitted, or a session key is exchanged, the arithmetic units perform the necessary field multiplications, squarings, and additions behind the scenes. The control logic sequences the steps, moving data between storage, computation, and communication interfaces with microsecond-level efficiency. The processor's flexibility extends to a wide variety of elliptic curves and field sizes, including the most widely adopted curves specified by standards organizations. The ability to adapt to different parameters is important not only for interoperability, but also for meeting changing security requirements as new vulnerabilities are discovered and new cryptographic techniques are developed. In mobile cellular networks, the processor must handle large volumes of authentication and encryption requests as users move rapidly between network cells. The fast scalar multiplication routines, projective coordinate systems, and efficient inversion algorithms described in earlier sections enable the network to respond instantly to these demands, maintaining seamless connectivity and strong security even at high user densities. Wireless local area networks, particularly those that span multiple administrative domains, depend on cross-domain authentication protocols. The cryptographic processor enables the rapid and secure exchange of credentials, derivation of session keys, and enforcement of access controls, all essential for providing a seamless user experience in environments such as universities, airports, and enterprise campuses. Sensor networks, increasingly important in industrial automation, environmental monitoring, and healthcare, require special attention to power consumption and computational efficiency. The lightweight arithmetic units, minimal memory usage, and deferred inversion strategies allow even the smallest battery-powered devices to participate in secure communications, ensuring that sensor data is protected from tampering, interception, or unauthorized access. Beyond these primary applications, the processor is also capable of supporting advanced features such as intrusion detection, secure routing, and countermeasures for known and emerging attack vectors. It underpins systems that can analyze network traffic for anomalies, defend against denial of service and jamming attacks, and dynamically adapt security settings to evolving threats. This high degree of adaptability and performance is not the result of any single breakthrough, but the culmination of years of research into both the mathematics of elliptic curves and the engineering of high-speed, resource-efficient hardware. By translating complex theoretical concepts into practical, deployable solutions, this cryptographic architecture makes robust wireless network security achievable on a global scale. Wireless network security continues to evolve as new types of devices, services, and applications emerge. In the face of rising complexity, the principles of high-performance elliptic curve cryptography, robust hardware design, and adaptive protocols remain central to protecting communications. This adaptable architecture is now deployed in environments ranging from traditional mobile networks and enterprise wireless local area networks to cutting-edge sensor networks and critical infrastructure. Each context brings distinct technical challenges, but all rely on the same fundamental cryptographic processes to establish trust, safeguard privacy, and ensure continuity of service. Ad hoc networks, for example, must operate securely without fixed infrastructure. Here, devices spontaneously form networks, exchanging cryptographic keys and verifying each other's identities on the fly. The cryptographic processor provides the muscle for pre-authentication, real-time authentication, and the secure distribution of keys, even as network participants come and go. Countermeasures against a wide spectrum of attacks, such as spoofing, eavesdropping, and unauthorized data manipulation, are integrated into the processor's routines, ensuring that the network remains resilient even in the most unpredictable conditions. Sensor networks push the boundaries of resource efficiency. Deployed in medical monitoring, industrial control, or environmental sensing, these devices operate with limited battery life, processing power, and memory. The streamlined hardware, optimized field arithmetic, and deferred inversion methods built into the processor make it possible for even the smallest sensors to participate in cryptographically secured networks. Specialized protocols protect the integrity and confidentiality of sensor data, enforce authentication of commands, and manage access control, all without draining critical system resources. In cellular networks, the cryptographic processor's high throughput is vital for managing millions of user authentications and encrypted voice or data sessions. As users move rapidly between cells or administrative domains, fast and secure handoff protocols become possible only with a hardware engine capable of real-time cryptographic computation. This ensures that communication remains private and uninterrupted, even as users traverse large or densely populated service areas. Wireless local area networks benefit from features such as cross-domain authentication and roaming, made practical by the cryptographic processor's support for complex protocols and rapid session key derivation. By efficiently handling multiple simultaneous authentication requests, the hardware enables seamless transitions for users moving between network zones, institutions, or service providers. Security is not static. Attackers constantly seek out new vulnerabilities and develop more advanced techniques. The processor is designed with this in mind, supporting upgradable cryptographic parameters, flexible field sizes, and programmable control routines. As standards evolve and security demands grow, the architecture can be adapted or extended without fundamental redesign, ensuring long-term viability for deployments across all sectors. Practical performance data confirms the impact of these design choices. Field programmable gate array implementations of the processor have demonstrated that complete elliptic curve scalar multiplication can be completed in less than a millisecond, even when operating with large field sizes and demanding cryptographic standards. Such performance is essential for real-time authentication, secure messaging, and encrypted data streams, requirements that are only becoming more stringent as network speeds and device counts increase. Ultimately, the processor's combination of flexibility, efficiency, and power creates a foundation for secure wireless communication in any environment. It supports not only current protocols, but also the innovations of tomorrow, such as advanced intrusion detection, real-time security analytics, and fully autonomous network operation. The ability to scale across device types and network models, from a single wearable sensor to a global mobile service provider, demonstrates the enduring value of this integrated cryptographic approach. The architecture and principles that underlie secure wireless network communication today are the product of a deep integration of mathematical theory, hardware engineering, and practical protocol design. At every layer, from the field arithmetic engines at the core of a cryptographic processor to the top-level security protocols that enable safe user authentication and encrypted data flows, each component is meticulously tuned for speed, efficiency, and adaptability. The result is a system that empowers wireless networks to meet the ever-growing demands for privacy, integrity, and resilience in a rapidly evolving digital landscape. This cryptographic architecture's most significant achievement is its ability to combine theoretical advances in elliptic curve mathematics with practical resource-conscious hardware implementations. Through the use of binary field arithmetic, projective coordinates, optimized inversion algorithms, and advanced scalar recoding, the system delivers exceptional performance in scalar multiplication, the operation at the heart of wireless security. Whether used in point addition, key agreement, digital signatures, or encrypted data transfer, every cryptographic routine benefits from these engineering optimizations. Scalability and flexibility are hallmarks of this design. The processor accommodates multiple field sizes, supports a variety of curve parameters, and adapts to new security standards as they emerge. Hardware accelerators built on this blueprint can be deployed in countless wireless environments, from smartphones and laptops to embedded industrial controllers and ultra-low power sensor nodes. Upgradability and parameterization ensure that the architecture is future-proof, able to evolve alongside advances in both cryptography and wireless network technology. The impact of these advancements extends far beyond theoretical research or lab-based prototypes. In the field, cryptographic processors, is based on these principles, are the silent engines protecting billions of transactions, authentications, and data transfers every day. From securing personal information on mobile devices and safeguarding industrial automation systems to enabling encrypted communications for national infrastructure and supporting the global expansion of the Internet of Things, this architecture is foundational. Perhaps most critically, this approach to wireless network security recognizes that threats and requirements are not static. The relentless pace of technological change means that new devices, protocols, and attack vectors appear continuously. The adaptable, modular nature of the cryptographic processor and its control logic enables networks to respond quickly, whether by upgrading cryptographic parameters, deploying new protocols, or integrating additional security features such as intrusion detection and anomaly analysis. As wireless networks continue to grow in size, scope, and importance, the demand for robust, scalable, and efficient security only increases. The cryptographic architecture described here, grounded in efficient field arithmetic, flexible control, and seamless integration with higher level protocols, forms the backbone of secure wireless communications for the modern world. It ensures that trust, privacy, and security remain possible, even as digital connections proliferate and society becomes ever more reliant on the invisible infrastructure of wireless data.